Eamonn Keogh from UC Riverside is here to talk about data mining time series and images. And as usual, this talk is going to be archived on Google Video, so please don't say anything confidential. Okay.
Thanks, Monica. Thanks for hosting me, and welcome to the talk. So let me give a quick outline. The first half of the talk is going to be kind of more or less a review. I'm going to talk about a quick review of time series data mining, and a way of looking at it, the generic data mining algorithm. And I'm going to show an explicit representation of time series data called SAX. And again, this is all kind of review. And then I'm going to talk about, in the next half of the talk, some new work we're doing in mining shape databases. And in particular, two problems: shape discord discovery, that's kind of finding unusual shapes, and shape motif discovery, which is finding near duplicate shapes. And if I have time, I have a little kind of a DVD bonus feature, which I'll try and get to also. So let's get right to it. First of all, what is a time series? I apologize. Oh, OK. So what is a time series? A time series is simply a collection of data collected sequentially in time. And so here's an example here. And of course, the beauty of this is actually we can plot this, and we can now see it's actually a heartbeat, and maybe even know what kind of a heartbeat this actually is, what kind of anemia is. So for the rest of this talk, I'm going to actually tend to show pictures more than equations and numbers. Hopefully, you'll go along with that. So I want to spend 10 minutes making the following point, that time series are ubiquitous. They're really absolutely everywhere. And the reason why this is the case is because people tend to measure stuff. We measure how many web clicks we get. We measure our popularity in Google. We measure whatever it is. And things change over time. So for example, George Bush's popularity changes over time, down, 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 down. And your Google stock changes over time, hopefully up, 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 up. And so the world is full of these time series in medicine, science, arts. But the other point I want to make over the next 5 slides is time series are ubiquitous for another reason, because many kinds of data which are not time series can be kind of massaged into becoming a fake time series. Let me show you 5 examples. So here's example 1. I took the Bible as a long sentence, and I took a window of length 100 words, and I split it across the Bible. And I'm going to measure the local frequency of certain words. So for the first example is God. So for example, in Numbers, God is hardly mentioned. And in Deuteronomy, it's all God all the time. So this is like a pseudo time series, and I can use this for various tasks. So here's one task. If I want to translate the Bible into Spanish, or sorry, I actually want to retrieve the Spanish text, I can look for a time series similar to the blue one, and I find in Spanish I get the word Dios, which of course is translation for God. Now this is actually kind of a trivial example. There's probably better ways to translate text, but this could be actually a bursty time series to say weblog clicks, and I could find certain words associated with other kinds of queries. Oh, sorry.
Why is there a difference between the two?
Okay, I was going to gloss over that, but I mean to zoom in for fun. So actually, when I did this originally, I noticed actually the match is overall quite good, but in one local area, there's actually quite a difference here. And so the question is, why is that difference there? So I subtracted the red from the blue, and I queried on the difference of those two time series. And the closest match is actually this thing right here, which is El Senior, the father, a synonym for God. And so for some reason, El Senior is a synonym for God, but it's kind of locally bursty. It doesn't happen in the Old Testament very much, but it happens a lot in the New Testament, particularly in Ezekiel. So it's actually a nice extra bit of value we can get out of this sometimes. Here's an example which comes back to later, but I'll kind of briefly show you now. We can also take shapes and convert shapes into time series. And again, one reason for doing this is because we have a big arsenal of tools that handle time series very well, that don't work well in video or shape directly, so we can actually handle things more efficiently in this space. Yet another example. This is actually every professor's worst nightmare, a grad student with a gun. So in this case, actually, on the top video, the grad student is pointing over there, and here's 3 examples that are over there. Here I'm tracking her hand. And in the bottom example, she's pointing a gun at somebody, and here are 3 examples of the gun. And in this example, if you look at the time series, it's easy to actually figure out which is which, because there's a little bump here you can see, which corresponds to the hand pausing over the holster and then drawing the gun out. So we can easily classify this in the time series space, but it's actually hard to do in the original video space. This is, of course, a very contrived example, but for example, in Las Vegas, there are similar moves you can make with your hand on a blackjack table that people actually want to know about automatically. Here's another example of a data set which is not time series, but we can kind of fake into becoming a time series. So here's a handwritten archive. I'll just briefly mention, I know Google's interested in doing this because I was in Dublin giving a talk in November, and halfway through the talk, the dean of the college kicked the door in, and he said, "Google has given us the check." And the whole room went wild. So obviously giving these guys too much money. Anyway, if we want to actually index this, we can transform it a little bit, remove the slant, and then we can make a pseudo time series, one above the word and one below the word, and then simply index the time series, which we can do very, very well. It's a very simple, naive thing, but it actually works much better than Markov models and these other tricks in this domain. Yet another example, I'll go very quickly over this, but here we actually have a four-dimensional brain volume, and of course it's not a time series, but we can actually fill the volume with a Hilbert curve, measure the local intensity at every part of the brain, and then take the Hilbert curve and stretch it out, as I've done here, into a kind of a pseudo time series. And once again, the idea is simply that we can't handle efficiently this high volume data, but we can handle a one-dimensional time series very efficiently. So the conclusion from all this is that there really is time series all over the world, in every kind of domain, and now let's do something interesting with it. So what should we do with this time series data? Well, we actually want to do everything with it. We want to do clustering, maybe cluster similar customers, similar web clicks, etc. We want to do classification. Is my heartbeat normal or abnormal? We want to do motif discovery, perhaps. So this is basically, are there any repeated patterns in this time series? We want to do rule discovery. So rule discovery might say, if ever you see a double peak like this, then within 10 seconds, we're going to see this shape here with some support and confidence. We may wish to do query by content. Basically, we want to Google time series. Many time series data sets are very, very large. So we actually want to visualize massive data sets. And finally, novelty detection. So here's a heartbeat, and something strange and novel happened here. The person either died or the machine got unplugged. So these are a diverse set of problems, but they all have one thing in common. To solve these problems, we need to actually figure out how to measure similarity. If we can do that in a meaningful way, all these problems, I claim, are trivial, but if we can't do this in a meaningful, useful way, then all these problems essentially are impossible. So let's talk about similarity very quickly. So the classic similarity measure is Euclidean distance, and here's the equation, but the picture is very simple to see. We have two time series, C and Q. We put them top of each other by Z normalization, and then we can simply measure the distance between the ith point, I to I, take that distance, square it, sum it up, square root of it. That's the Euclidean distance. Euclidean distance is very simple, but it's amazingly effective. You have to do an awful lot of work to actually beat this. This is incredibly simple and easy to do. Again, we're doing kind of a review here at this point. We'll get to the new stuff in a moment. So one thing about data mining is that most of the time in data mining, you're actually going backwards and forwards from disk. CPU time is typically not even relevant. It's all disk access time. So to handle that, most data mining algorithms don't work on the original raw data, whatever that is. They work at some kind of abstraction of the data. So here we have a time series in red, but we can't fit it into main memory. So we're going to put instead this blue abstraction of it, and that will fit into main memory. So here's one example of an abstraction. I'll show you others in a moment. One important idea is that if we want to measure the distance, let's say, between Google stock and Yahoo stock, and we can't fit it all into main memory, we can actually have the approximations in main memory, and we can measure the distance approximately in this space. Again, a simple and useful trick. Now, of course, the piecewise linear approximation is only one approximation we could have used, right? We could have also used wavelets, Fourier transforms, SVD, et cetera, et cetera. So we actually have many, many choices of things we could do. OK, now I'm ready to show you the generic data mining algorithm. And this basically works in principle for anything I've shown you: indexing, classification, clustering, rule discovery, et cetera, et cetera. It's a kind of a basic generic paradigm for mining data. The first thing we want to do is we want to create an approximation of the data which actually fits into main memory. So we can't fit all the data into main memory. We're going to approximate it and then fit into main memory. And now we're going to, in main memory, approximately solve the problem at hand, whether it's rule discovery, et cetera, et cetera. At this point, then, we have an approximate solution, which might not be exact because we're working on an approximation of the data. So in the next step, we're going to go to disk, hopefully only once or twice, to either confirm the model or to slightly modify the model a little bit. And the hope is that we're going to make very few accesses to the disk in this stage, rather than many, many accesses we would do if we worked in the raw data. So if you believe this model, then all you have to answer is, which approximation should you use? And there's lots of approximations out there. This actually, I think, is a complete taxonomy of them. And don't worry if you can read this, it's not really important. The point is, we have lots and lots of choices, and which one should we pick? There is one very, very important requirement for any approximation we use, and this is lower bounding. It turns out that if we do this generic framework, and our approximation obeys lower bounding, which I'll explain in the next slide, then when we do this, we can guarantee the answer we have at this point is identical to the answer we would have gotten had we actually looked at the raw data and done all its accesses, right? So this is actually a very nice result. Again, all I'm saying is that if the approximation obeys this lower bounding principle, I can do this very efficient thing and end up with the same answer as I would have gotten on the raw data. So what is this lower bounding thing? Well, we've seen we can measure, for example, Euclidean distance, right here, but again, I can't fit all this raw data into main memory. So suppose, for example, I had a piecewise constant approximation, which does fit in main memory, and I measure the distance approximately on that space here. So here's a measure for it. Lower bounding says that for any possible two objects, Q and S, that the distance in the reduced space is going to be less than or equal to the distance in the true space. Hopefully, it's going to be very closely approximating it, but the important thing is it's always going to be less than or equal to. If this is true, again, we can now use generic data mining paradigm. Now, there's lots of approximations I mentioned. This is not even a complete list, but one of them is kind of special, symbolic. And although there's lots and lots of ways of taking a time series like this and convert it to symbols, I have counted at least 200 different ways of doing that. Unfortunately, none of them lower bound. In contrast, I can lower bound wavelets, Fourier transforms, SVD, et cetera, et cetera. I can lower bound all of these, but unfortunately, of the 200 ways out there, none of these actually lower bound in a symbolic space. So why do we care? Well, just think about what you can do if you can actually use symbols, right, that you can't do in the real space. So for example, I can hash symbols meaningfully, but you can't really meaningfully hash real-valued numbers. I can use suffix trees and symbols, which again, you can't really use on real-valued things. Markov models, for example. More generically, there are lots of people out there who are experts in dealing with symbols. People at Google, for example, or people in bioinformatics who are used to dealing with 4 symbols all the time. And they have wonderful ideas, algorithms, data structures, et cetera, et cetera. And if I can actually have a symbolic representation, I can steal all their wonderful ideas. And again, I can't really do this in this real space. So a contribution I want to talk about briefly is we have created the first symbolic representation of time series that actually allows lower bounding of the Euclidean distance. And this means we can do all kinds of wonderful, clever things. I'm going to give you some examples in a little bit. So our representation is called SAX. And again, for clarity, all I'm claiming is this, that you can give me a time series like this one here. I can put it to my little magic black box, and I'm going to spit out a symbol string instead. And furthermore, I can measure the distance between 2 sets of symbols, and this will be a lower bound to the true distance in the original raw space. And if this is true, then I can use all these wonderful algorithms and guarantee I get the right answer with my generic data mining paradigm. So the obvious question is, how do you get SAX? Okay, it's quite simple. We have the original time series here in blue, and I'm going to simply take a window of a fixed size and measure local areas, look at the average. So here's the average of this section, the average of this section, and so on and so forth. It's a piecewise average approximation. Once I do this, I'm going to take a little Gaussian curve here. I'm going to divide it into 3 equal areas. So the area here, the area here, and the area here are all equal. And I'm going to extend some breakpoints out. And anything above this breakpoint is a C. Anything below the breakpoint is an A, and in the middle here it's a B. So I can take this real value time series in blue and eventually spit out these symbols here. So let me preempt a question people often ask. So why a Gaussian? It's true that for long global time series, they may be actually non-Gaussian. But for small local subwindows or virtually any time series, they do tend to be approximately Gaussian. And we've seen this actually in 120 different data sets in very diverse domains. So here's kind of a visual kind of proof if you like. And again, I can show you this in many, many different data sets. So the idea is, by using this technique, we guarantee that we have approximately equal symbols. We have as many A's as B's as C's. And most things we want to do, like Markov models and hash and suffix trees, have their best cases if you have equal number symbols, equal probable symbols. So,
Is it only limited to 3?
no, this is actually arbitrary, and we can choose a number of symbols we want to use. One thing,
This function is just to discretize the data, though, right?
that's all it does so far, yes.
It could be linear, or it could be any other distribution.
It could be. So actually, we thought about making this adaptive at some point originally, but when we made it adaptive, it always became a Gaussian, basically. So we simply hard-coded that fact. I should say actually that if this actually is a non-Gaussian time series, then the correctness of all the algorithms doesn't change. Everything is still correct. It might be less efficient, right? But we're pretty safe there. Here's a quick visual comparison. Here's a time series, and here's a SAX representation. And visually, here's a comparison with these other approximations. Visually, we don't really lose anything, right? The reconstruction error is about the same in most cases. I can always find you some examples that make one of these look better than the other, but on average, it tends to be that SAX actually works as efficiently as the other things in terms of reconstruction error. Again, I told you there's a lower bound here. I'm not going to actually prove it or derive it, but I want to re-emphasize it actually is true, that the Euclidean distance between two time series is measured like this, as we discussed. And in the SAX space, this function here, the min function, actually gives us a distance which approximates this distance and will always lower bound. And we can prove it by transitivity. Basically, this is known to lower bound this, and we can show that we can lower bound this. So we now we have a lower bound representation.
Intervals, is it unit terms or your
So there are two parameters in SAX, right? One is the cardinality alphabet, A, B, and C is 3, for example, and the other is the number of sections here. And there are choices that have been made here, unfortunately. Although actually it's not critically sensitive, those choices in most cases. Okay, just a bit of a history of SAX, and then we're going to get onto this new stuff with shapes. So it was invented in 2002, and the first thing we did was we showed that for most problems, it basically works as well as Fourier transforms and wavelets, et cetera, for all the classic but boring problems, classification, cluster, and indexing. And then in 2003, we showed that actually SAX allows linear time discovery of time series motifs. So if you have a time series and you have a repeated pattern in it, we can actually find those in linear time. It's been referenced 60 times, but actually most of these times are actually applications of this. People now use this technique for motion capture. They use it for telemedicine, mining medical data sets, and whatnot. So people actually really do use this quite a lot. And in 2004, we showed how to use SAX to do parameter-free data mining. Last year, we had a real explosion in things we're doing with SAX. So we're doing anomaly detection, visualization of massive data sets, joining streams, et cetera, et cetera. And recently, for example, this year's KDD, there was many papers actually submitted, at least, that use SAX as wavelets and Fourier transforms. So I really think that SAX is getting some critical mass here. It's going to actually take off quite a bit. So this has all been review. Today I'm going to show you that with SAX, we can actually now do data mining on shape data sets and do very interesting things in that domain.
Is the Gaussian here a key point in the proof of the lower bound?
No, any distribution is fine, yeah.
So uniform is fine.
Any distribution you want, uniform is fine, right? But in general, Gaussian will give you equal probable symbols, and uniform will not. But the A's will be very rare, and the B's will be more common, and then up the other side of the alphabet, those symbols will be less common.
But, I mean, isn't it the uniform, I mean, if we do a uniform distribution, this is like the simple approach to represent the time series simple, right? I mean,
Uniform, actually, we can handle uniform if you want, but in general, virtually every time series has this Gaussian property. It's kind of hard to believe, and reviewers often don't believe it. So I actually built a web page, and for 100 data sets, we showed it's true, and 100 data sets empirically, and we kind of point reviewers to that. People's intuition tends to be wrong there. Again, globally, most time series are not Gaussian, but small local windows virtually always are.
okay, here I misunderstood.
Okay.
Intuitively, when I like to represent my time series as symbols,
Yes.
what I will do is simply the same, maybe not piecewise linearization, but I will take like the high values and name them A, B, C, D with uniform distribution.
If you do that, you will have symbols that have different frequencies. And you generally don't want that. You generally want to have equal frequencies because, again, for Markov models, for hashing, for suffix trees, it's always better to have equal probable symbols. But you could do that if you wanted to, and SAX would allow that if it wanted to. That would be fine. Question?
Yeah, I think you answered it. Like, why do you want the improbable symbols? Because the lower bound becomes closer to the upper bound if you have?
Empirically, that's true. You can't prove it because there could always be a special case that's not true for. Empirically, that is the case, that the lower bound is maximally tight, and that's true, yes.
But also, I mean, this relies on the shape of the time series. I mean, if the time series starts in a very low values and then it grows larger and larger, you will need more symbols to represent this time series.
The symbols, the number of symbols is fixed as a user choice, as a user parameter. So that isn't the case.
I mean, if I fix the number of symbols to be only 3, for example.
Yes.
Okay, I will guarantee that the number, the frequencies will be similar, but I mean, 3 is not enough for this time series. So I mean, is there a way to figure out which number can fit this time series more on a literal measure?
In general, we impose 3 or 4 as the number of symbols, but actually you could try to learn it using, say, minimum description length or some technique like that, and we've done some work on that. It's not very motivating because we found basically 3 symbols. Virtually any kind of problem, for any kind of data set, tends to work the best. So we didn't really have to make SAX kind of adaptive to different distributions, different kind of symbols, but really it becomes a waste of time. The simple thing just works amazingly well. So I hinted this earlier on, but I want to show you again in more detail, that we actually can convert time series, we can convert shapes to time series. So here we have a shape, and all we do is we find the center point, the mean value of the shape, and now we're going to actually have our clock hands go around 360 degrees, measure the local distance here, and that local distance becomes the height of the y-axis. So some observations about this. First of all, there's other ways of doing this, but this way actually I like quite a lot because, first of all, there are no parameters. It's completely parameter-free. It's very fast and easy, and it's very, very intuitive. So why do this? Why take shapes and map them into time series? Well, again, there's a whole arsenal of tools we can use in time series space. Let me give you some quick examples. This is the famous Brotman image of 2 howler monkeys, kind of idealized. Here's the real deal. Here's some real howler monkeys. And you actually can see that Euclidean distance here will really be quite intuitive, that a howler monkey is going to be very similar to a similar howler monkey, and Euclidean distance can reflect that, and life is good. So if we actually query with this, we'll probably find this thing here. Another tool in our arsenal is dynamic time warping. So in some cases, actually, the shapes might be morphologically changed. So for example, different gorillas might have a different prominence of the brow ridge or a different prominence of the jaw. But in a time series space, that simply becomes the fact that these peaks move backwards and forwards in the x-axis. And again, we can beautifully handle that with something like dynamic time warping.
Question, if there are phase shifts, so how do you align the stuff? Because
so another time, it's great questions. I think the question is rotation invariance, basically. So if one skull is rotated around 90 degrees, lovely. We absolutely can handle that, but I'm going to just push that aside for a moment. I actually brought some papers to show you, or we can talk about it offline. This actually is a general question. How do you make sure that the 2 skulls are aligned in the right direction? And for the moment, I'm going to ignore that, but we actually can handle that easily.
Why is the purple line across the orange?
It looks weird, but it's simply because you can't. Everything actually maps correctly, but this because one's above, one's below, basically, it's topologically changed around. It looks distorted at first, but if I took this one here and I pulled it down here on top of each other, the lines wouldn't cross.
Oh, I see.
It's a bit visually distracting, but if I took this and pulled it down here, life would be good.
You also talk about how you deal with compression and expansion. Like if you change the tick, like the angle per tick for getting this time.
Oh, sure. Well, for simplicity, we simply normalize these to be all unit length. So the size of the shape makes no difference. Obviously, if I have a skull that's 5 times as big as another skull, it's probably just that the photograph is taken from a different distance. So we normalize them to be all unit length, basically. Sometimes even dynamic time warping isn't enough. So this actually is the famous School 5 skull. And when you actually see it in universities, typically you have this example here where they filled in the missing parts of some epoxy. But the real actual skull that was found is basically missing all the nose region. Now, if I want to match this, it's problematic because if I insist upon matching the miss and nose region, I'm going to get pathological results. So once again, in the time series arsenal, we actually have a tool, longest comes up sequence, which basically says, try to match this shape, but if it's too hard to match something, basically give up. And so here, it matches everything beautifully, but just the nose part, it essentially gives up on that part here. It knows it's like a wild card. I'm not going to match this. So again, here's some examples to simply show that we can actually take these shapes, convert the time series, and then throw lots of different tools at them. But I wouldn't point out actually the Euclidean distance tool works exceptionally well by itself. So here's a cluster of primate skulls based upon the Euclidean distance, and it's not the correct evolutionary tree. So for example, the humans here should be closer to the orangutans, obviously. But it is subjectively sensible, and at the lower levels of the tree, all these red things here, all these blue things here, etc., it is actually giving us the correct subtree for the tree of life. Notice, by the way, that the humans are an outlier here because of a massive brain case. So again, the point is simply at this point is that we can take shapes, give up the time series, and then we can meaningfully measure similarity in that space. Once you believe that, well, now we can actually do some real original data mining on shapes, and again, this is some ongoing work. We're going to show some interesting things we can do with shapes. So the first thing I want to look at we call image discords. Let's say I give you a database of shapes, could be quite large, and the question is, what's the most unusual shape in the collection? So you can look at this visually, probably most of you will grab this one here, and this is actually the correct answer. That was somewhat subjective, so we actually have an objective definition to this. We call it shape discord. And the intuition is we want to find the shape which has the maximum distance to its nearest neighbor, right? So in terms of islands, you think of Hawaii as being a discord, right? Its nearest neighbor state is probably California or Alaska, which is very far away, whereas Nevada has a very close nearest neighbor. So of all the possible shapes in here, which one has the maximum distance to its nearest neighbor? And it happens to be the shape right here. So why is this useful? Let me show you some examples. So here's a fairly large collection of fruit fly wings, and often people modify the genes and then see what difference it makes in the phenotype of these insects, right? And actually, if you get the wrong gene, like a LOX gene, you can actually make an antenna sprout out of the wing bud, for example. So in this case, actually, we mined this, and this one popped out here. It's clearly not a phenotype. It's simply someone damaged the wing, basically. But the point is that we can actually find this unusual shape quite efficiently, as we'll see. Oh. It is somewhat similar to outliers, but there are some kind of differences. Outliers in Euclidean space are easy to find, roughly speaking. But in this case, because we have a rotation invariant metric, we can't actually embed them into Euclidean space directly, as we'll see in a moment. But it is somewhat similar to outliers, yes. So here's another example. Here we have a very large collection of petroglyphs, basically ancient graffiti. And we want to actually find, are there any unusual shapes in this data set? This, of course, is a subset of it. And so we found the number one discord here is the shape right here. And so the question is why? If I pick a different shape, let's say this one here, and look at its nearest neighbor, which happens to be this one here, you can see actually they quite match very well. Some small local differences, but they're basically very similar. And this is true for almost all of them. They have some similar shape in the database. But this one here doesn't. Why is that? So here's actually the red one and the blue one together. There's a local difference here. And the explanation is that this one uniquely has an arrow sticking into it. It's a bighorn sheep, and someone stuck an arrow into it, which caused this large increase in the time series space here. As it happens after visual checking, this is the only one that actually has this arrow in it. Two more quick examples. Here's a collection of projectile points or arrowheads. And it's hard to overestimate how many of these things actually are. At UCR alone, we have 1 million of these things. Unfortunately, most of them are not photographed or indexed. But with a small subset of these, a few thousand of them, we run the algorithm, and it pops out this one here. And actually, I was quite surprised to know that arrowheads can be asymmetric. And finally, some kind of special fishing tools look like this. And this example right here is a subset of a large cell we looked at, a large slide we looked at. And most cells, blood cells, tend to be round, which is like a flat line in time series space, or a figure of 8 shape. This basically corresponds to either 2 cells put together or a cell dividing. And again, this is not unusual because it looks like this, and that's not unusual because it looks like this, and so on and so forth. But one of them, this one right here, which comes from here, is unusual because actually it's teardrop shaped. and it has no near match in the data set. And as it happens, I think teardrop shapes are indicative of a kind of anemia, basically. So I'll touch on examples right now. Hopefully you believe that this definition can be useful for looking at large data collections. I guess the question is now, how do we find these things efficiently? Well, first of all, how do we find them in general? Here's the actual MATLAB code. It's very simple to find them, but unfortunately, it's very, very slow. So let me explain the algorithm by looking at this matrix. We don't really need to build a matrix. We can actually simply compute things on the fly, but it's easier to understand if we actually look at the matrix. So the code basically is two nested for loops, which simply walk across each column, and then within each column visit every single row. And they look for the smallest value apart from the diagonals. So here I come down, I find that in this column here, 1.1 is the smallest value. That's my best so far. And I keep looking for those. At this point, I'll find here that 7.5 is the smallest value in this column, and it's actually the largest, smallest value. So in this case, this is actually the discord in column 6. So the good news is it's a very simple, trivial algorithm. The bad news is, of course, it's quadratic. It's actually constant space, because I don't have to keep this in memory, but I actually have to visit all the cells here to have a quadratic algorithm. And the question is, can we do better than that? And the answer is, of course, yes. So one simple observation is going to help us here, which is, suppose I'm searching across here. So I've found in this column 1.1. That's my best so far. And then here, for example, I find 2, which is my best so far. When I get to the next column, as I scan down, if I find a value here, apart from the diagonal one, which is less than my best so far, I can stop. When I find the 1.2 here, I know there's no point in continuing on because this is not going to be the discord, and so I don't have to visit this cell or this cell. So a very simple pruning technique can help us quite a bit.
But to begin with, it's quadratic because you need to have like a matrix.
We actually have to, so in this simple example, I'm showing the whole matrix is actually constructed. But of course, we don't really construct the matrix. We kind of build it on the fly. We measure distances on the fly. OK, so this actually potentially could help a lot. And there's one other trick that could help us quite a bit. We can actually have heuristics called outer and inner, which tell us the order in which to visit these columns. So I'm assuming a for loop right now that goes from left to right and from top to bottom. But I could simply permutate that and go in any permutation. I could visit this one, then that one, then that one. And then within each column, I can visit this one, then that one, and this one, etc. And if we're very careful, this will make a huge difference, right? If we actually visit them in a special order, things get a lot better. How much better? Let's imagine a magic heuristic, which is given to us by God, right? What would a heuristic actually do? It would tell us that we should visit the columns in order of discord value. And in other words, we should actually jump to the real discord first, and then the second best discord second, and so on and so forth, right? If that happened, then we would find a large value here, 7.5, early on, and we could do very good pruning. And likewise, for the inner heuristic, if we were magical, what we would do is that when we got to a column, we would jump to the smallest value right away. We'd go straight to the nearest neighbor, and it would be less than our best so far, and we could stop. We would have to look at the rest of the things in the column.
But still, to find the minimum, you need to calculate everything in a column, which means...
Yeah, so the analysis basically is this. If we had this magical algorithm, right, the first column we went to, we'd actually visit every single thing. That's order of n. And then an order of n number of times, we make one constant move. We jump to the nearest neighbor, we'd stop. So basically it'd be 2n, which is linear.
But we don't know the nearest neighbor until...
No, I agree. So this is a magical algorithm. This is what God can do. We can't do this. OK. So if we were magical, and God has given us the heuristics to order these things, we'd actually go from quadratic to linear, right? So life potentially is very good, but the question is, can we actually do this? So the answer is we can't actually do it, but we can approximate it very closely. So the two observations are this, that although we like to visit the columns in this magical order, as long as we actually get a reasonably high value early on, it really makes no difference. So early on in our first few attempts in the outer loop, we want to find a pretty high value here. And if we do that, we can prune quite well. And the other observation is that for the inner loop, we don't really have to jump to the nearest neighbor in constant time, as long as we jump to a near enough neighbor. A neighbor that's actually less than the current best so far. So if it's the 5th nearest neighbor or the 20th nearest neighbor, it might be near enough to stop. So based on these two observations, we're going to try to approximate the magic algorithm.
So is this basically annealing then, or simulated annealing, where you're just picking a random value and then trying to jump around the space to find a lower?
No, we can do better than random. I'll show you. So the answer to this problem is actually going to be based upon SAX. What else? We take our shape, convert it to a time series, convert it to SAX. And now we're going to put these SAX words, CAA, into this little matrix here. So this is the first shape, CAA, and so CAA goes here, and I guess the next shape was CAB, and that goes here, and so on and so forth. So I'm going to populate this little matrix here. As I'm building this, I'm also going to insert these words into a suffix trie. So for example, image 1 was CAA, and I put a 1 here because image 1 came from there. And then for image 2, CAB, I put a 2 here. And for image 3, it's also CAA, so CAA, I have an overspill, I have a 3 here. Okay, so I hope you believe me that actually I can build these in linear time and basically constant space, in fact a very small constant space. So in linear time I've built these, and I'm going to use these to approximate magic. So the first question is, I want to visit the outer loop where I'm going to find a likely discord very early on. And how do I do that? Well, I have this count here, 1, 2, 3, and I can map it back into here. So everything that is here, CAA, this one here, gets a value of 3, this one here gets a value of 3. This is simply a count of the number of words that happen to map to that particular, the number of those words. So the intuition is that if I have an unusual shape, it probably had an unusual time series, which probably had an unusual SAX approximation, so its count here is going to be very low. In contrast, if I have a very common shape, it's going to have a very similar time series, very similar SAX words, and the count probably be very high. So my outer magic heuristic is going to be this. Find the smallest value in this column, and whatever that is, I'm going to jump to that value first. The value is typically 1, and if I have some ties, I'll jump to them, I'll take all the ties and go to those first. So my simple approximation to the magic outer heuristic is find a small value here and then go to those values first. In the inner loop, the same intuition kind of works here. Suppose I'm going to my search and I want to see if this is the discord, or if not, I want to find out very quickly. The intuition is I want to find similar things to it early on to be able to prune. And how am I going to do this? Well, similar things to this, CAA, are likely to be either 1 or, I guess, 731. Because they map to the same SAX word, they're probably similar, they probably have a small nearest neighbor distance, and I can actually abandon search early on. So this is my heuristic for the outer loop, for the inner loop. And my hope is with those two simple heuristics, I can actually approximate the magical algorithm. So this is kind of ongoing work. I don't have very detailed results here right now, but on a small data set, like 200 arrowheads, we find that we actually get within like 22% of the magic algorithm. And the good news is, for larger and larger data sets, we actually get better and better and better. We get asymptotically close to the magical algorithm. Essentially, we're solving a quadratic problem in linear time. Now, one small problem is that this is actually empirically true in all data we try, but in the worst case, it could still be quadratic. If you give me a database with every shape is identical, I'm in trouble, right? But for realistic data sets with some kind of variance, we actually get basically a linear time algorithm. Okay, let me show you a complementary problem, and I'll do this at kind of a high-level detail to be a little bit faster. Now we have a data set, and the question is, are there any duplicates in this data set, right? So trivially here, I guess, we have this and this duplicate. And then the question is, again, how can we find these duplicates and find them efficiently? And once again, we have a reasonable definition for this. Basically, we're trying to minimize the Euclidean distance between a pair of objects. And once again, the question is this useful? And I'm going to just be very brief and show you just one example. So here we have a data set of about 4,000 different petroglyphs from all over North America, including Canada and Mexico. And the question is, are there any similar ones? I mean, subjectively, there are similar ones, but what are the most similar pair in this data set? And actually, here's the answer. And it's actually quite interesting. First of all, notice actually we have to be rotation invariant to find this. So they're similar, but one's rotated 90 degrees. What's also interesting is actually that these two came from locations which are only 150 miles apart. So potentially there's actually some meaning to this, basically, although I actually don't know at this point. Okay, so image motifs are quite interesting in this example, but how can we find them? And again, for time reasons, we're going to just kind of gloss over this, but basically the idea is, once again, SAX. We can use a SAX representation, and as it happens, repeated patterns in DNA strings are very, very important. So we're going to steal someone else's algorithm, take our shapes, convert them to SAX, and then find DNA repeated patterns, essentially. And then because it's low bounding property, we give the data back to the generic algorithm, we do some cleanup work, and in basically linear time, we can find these repeated patterns using someone else's representation. And I think the important thing to point out here is that you can really only do this with SAX. It's hard to imagine how you do this with wavelets or Fourier transforms or anything else, because it relies upon the ability here of hashing in the random projection algorithm. Actually, I'm going to conclude here, but I have a 5-minute bonus feature, which I will try to get to. Is that okay?
I think so. So about 13 minutes.
Lovely. So conclusions, and again, I'll go on for another 5 minutes, but the first conclusion is, and you probably already know this, basically, right? The representation is everything. With the right representation, you can solve any problem efficiently. And for time series data mining, SAX is probably the best answer for most problems. But the nice kind of new result here, hopefully, is that SAX is also probably the best answer for all kinds of problems with shapes, too. And I really can't overemphasize this. I really believe that SAX actually is the way to go for virtually all kinds of problems in time series and shape data mining. You can just do things when you have symbolic representations that you can't do in the real space, and you can simply use so many clever tricks. Again, I will go on a little bit after this, but my kind of conclusion was going to be, if I didn't have enough time, SAX appeal. I'm always interested in new collaborators, and I'm always interested in new problems, new data sets, and of course, I'm always interested in money. Okay, so here's the 5-minute bonus DVD feature, if you like. We can actually use SAX to visualize very massive data sets, and here's how we're going to do that. Let's start with a digression. Here's some DNA from 2 different animals, and the question is, are they similar animals? Right? And obviously, there's no way you could tell by looking at this. And of course, it's actually a small subset of a genome, which is about 3 billion base pairs in a mammal. Let's try a little trick. Let's build a 2x2 matrix, and let's label them ATCG arbitrarily. And let's actually count how often we see those letters in a DNA sequence. So in this case, 20% of the time, we saw a C, and 24% of the time, we saw a T, and so on and so forth. I can actually make more complicated matrices, just basically recursively do a little trick here, and I can count every possible combination of 2, CC, CT, TC, et cetera, et cetera. And I can do this, of course, any level I want to if I want. And now I can count how often I see CCs or CTs, et cetera, et cetera. Having done this, I now have a matrix of numbers, and I can map those to colors. I can linearize all the colors arbitrarily from 0 to 1. And in this case, I see that this pixel here, for example, occurs 7% of the time. So I can look up 7% here and paint it red. Once I've done that, I have converted DNA string into a colored bitmap. And I guess the question is now, so what? Let's actually look at some files of DNA under Microsoft Windows, the classic thing, Notepad, I guess. And here are the icons for Homo sapiens, Loxodonta africana, et cetera, et cetera. And looking at this, you've no way of knowing, are these things very similar? But let's actually do this now with this trick I just shown you. Let's replace the normal icon with the icon I've learned with this approach I've shown you in the previous slides. When I do this, I see this. And it's strongly suggested that these 2 things look alike, and those 2 things look alike. And as it happens, this is the Indian elephant, the African elephant, and this is the chimpanzee and the human. So it's somewhat intuitive, it makes kind of sense. You can look at these bitmaps and figure out these are a pair and these are a pair. Okay, that was all a digression because I'm talking about time series. And the question is, can I do something similar for time series? And so what? Would it be actually useful? And the quick answer is, of course, yes. We have SAX in our arsenal of tools. And with SAX, I can make a string, a pseudo DNA string, if you like. And then once I have a pseudo DNA string, I can map it into a matrix. I can get the colors, and life is good. So I can do this very fast. The question is it useful? So here's the first example. Here are some brain waves from rats. And if you look at this, it's sort of like the Sesame Street game of which one of these things is unusual. And the answer, I guess, is this one looks different to those ones. As it happens, these are all epileptic rats, and this one isn't. Okay? let's try this. I can actually add value to this by mapping them into Euclidean space based upon multidimensional scaling. I'm basically going to find the similarities and kind of cluster them in two-dimensional space. So this actually data set is monthly power demand for Italian electrical power. When I do this, I see that actually all my winter months are over here, and all my summer months are over here. But one summer month, August, is completely unique. It's out there. So why does it look different, and why is it far from these things here? And actually, if you're Italian or if you're European, you might know this. In Italy, in August, the entire country closed down, field closes, the government closes, and everyone goes to the beach. And actually, we can see this if we plot the data right here. Now, of course, in this case, we can actually see this anomaly if we plotted the data. But I guess the utility of this is you can see anomalies without actually opening MATLAB or Excel, whatever tool that actually you have. And in any case, this anomaly here, or this cluster here, is too subtle to see, to my eye, in this space here. But we can actually see it better in this space right here. Here's another example. This is a famous data set, at least in data mining, for testing clustering algorithms. And it allegedly contains 70 heartbeats. Here's a subset of them. Once again, in the classic view, nothing really is added to the value here. But in the bitmap view, we see this. There appears to be two strong clusters. These guys here and those guys there. So what's going on? Why are these guys so different from these guys? As it happens, they're not heartbeats. A grad student many years ago made a mistake. So these 5 things here are not heartbeats. They're what's called pacemaker cells, but natural pacemakers, not electronic ones. So no one has noticed this, even though many people have actually used this data set for testing algorithms. And again, the value here is that we could actually find this if we plotted the data and looked at it, potentially, but we get it here for free, essentially. When we copy or paste or edit or move files around, for free we can actually see what's going on. This is my final example, and I'm all done for the day. My hope actually is to use this for basically almost like a Google toolbar tool for query by content. So I can search for documents based upon the data that was created, its file size, its type, etc. And I can also search based upon keywords. But let's think about a more general search. Search upon structure, where you simply say, find me a file that's similar to this one. Here's an example of that. It's kind of trivial and contrived, but it makes sense. Here I have a data set of large mammals in the Americas. And I right-click on the brown bear, and I ask for its nearest neighbor. And so we search quickly to an index, and the nearest neighbor is the polar bear. And you can kind of tell visually that actually they look similar, right? These two icons here, or bitmaps here and here. As it happens, last night on CNN, they announced that actually they had found the first polar bear, brown bear hybrid in the wild, which is kind of an interesting coincidence. So I've shown you actually I can take time series and map it into this, and I've shown you how I can take DNA and map it into this. And right now we're working on doing this for text, right? So using latent semantic index and something else, we convert text into bitmaps, and it actually works quite well. If you look at my papers, they all look kind of similar, because I only do one thing, basically. If you look at Shakespeare, it tends to look a bit different, and so on and so forth. And so the question is, could we actually use this to do kind of fast search by type? Basically, find me similar documents to this document right here. Great. I thank you for your indulgence. And now I really am finished, and so I'll be happy to answer any questions you might have.
So what are some specific application areas where you see this being applied? I guess you did refer to 40 references, 60 references to some of the...
You mean for the shape thing?
Yeah.
Well, one interest you've probably seen is anthropology. So anthropologists typically have lots of data. As I mentioned, 1 million arrowheads. In one part of Nevada alone, there's in like 10 square miles, there's estimated to be about 100,000 petroglyphs. And amazingly, people don't know anything about these things, surprisingly. So anthropology is one possible example. Definitely looking at things like cells in biology. It's very tedious to actually look at every single cell. The fruit fly wings actually makes a lot of sense too, because biologists make lots and lots of data like this. So those are some kind of potential applications. I'm hoping people will suggest more when this work kind of gets out there a little bit. Another example we're actually doing was we're looking at long video sequences of, say, martial arts. And the idea is we want to try and find 2 video sequences where the person actually has the same pose. If we have that kind of a collision, then we can actually run the video and then jump from one video stream to a different video stream. So basically, we can kind of make fake, it's called video textures, where we can combine different moves, kicks, and punches. People have tried this in motion capture data, and it's very, very hard to do. In the simple example we have with shape, unfortunately I don't have any with me right now, it actually works exceptionally well. So basically for video games, it's quite useful to do this, right? We actually have a kick and a punch, and we have a kick and a fall, and we can actually kind of combine those to get any combination of those, basically.
It seems like you're focusing on silhouettes also, instead of using more complex algorithms like Hilbert curves in 2D space or something like that.
So we are looking at silhouettes, obviously the simplicity. There are, for many shapes, you can look at silhouette and you can actually tell what it is. Virtually, it's always the case, right? Certainly people's faces, it's very easy to recognize people's faces based on that. For some shapes, of course, the color, the texture, or internal features are important. And currently we're not looking at those, but we have to do something to initially start this, right? So, but that is potentially future work. Any questions?
I wonder if you have any thoughts on applying your kind of anomaly detection to surveillance applications.
We do. For one reason, it's because it's very heavily funded and people kind of like that kind of stuff. So we actually are looking at anomaly detection in that kind of domain. So you can think about unusual shapes and trying to match shapes. So for example, even things like matching suitcases based upon the shape to figure out if it's been transferred between different streams and whatnot. So it's something we're actually looking at a high level, yeah.
If there's no more questions, let's thank the speaker.